close your eyes for just a moment. Imagine you're floating. Not in water, not in air. You're floating somewhere far beyond anything that has a name. There are no walls, no floor, no ceiling. There is no sound, at least not the kind of sound you're used to. And yet, all around you, something extraordinary is happening. Stars are being born. Stars are dying. Ancient light that left its source before your great-great-grandmother's grandmother ever drew her first breath is only now reaching your eyes. And here's the strangest part of all, time, the thing you trust more than almost anything, the thing that wakes you up in the morning and tucks you into bed at night. Time is not behaving the way you think it should. It's moving faster in some places, slower in others. In some corners of the universe, it almost seems to stop entirely. What if I told you that time isn't a fixed, steady drumbeat ticking the same way everywhere in the cosmos? What if time is more like a river, sometimes rushing, sometimes crawling, sometimes pooling so deeply that nothing can escape? What if stars are actually clocks, ancient, burning, magnificent clocks, and some of them have been ticking so precisely, for so long, that they put every watch ever made on Earth to absolute shame? And what if there are places in this universe, dark, invisible, terrifyingly powerful places, where time doesn't just slow down but breaks, where the rules of reality as we know them simply stop applying? Tonight we are going on a journey not just through space, but through time itself. We're going to meet the universe's most extraordinary timekeepers, from the violent birth of stars to the silent, patient spin of pulsars, from the warped edge of black holes to the slow, rhythmic breathing of the cosmos itself. You don't need a physics degree. You don't need to understand a single equation. All you need is your imagination and a willingness to let your mind stretch a little further than it has before. Because the universe has a story to tell. And it is far stranger, far more beautiful, and far more personal than you've ever been told. Let's begin. Part 1. How the universe tells time. The clock you never thought to question. Here's a question nobody ever asks in school. What actually is time? We all feel it. We all live inside it. We schedule our lives around it. But if someone walked up to you on the street and asked, "What is time, really?" Most of us would stutter. We'd say something like, "It's the thing that passes," or "It's what clocks measure," which, when you think about it, is a little bit like answering "What is water?" with "It's what cups hold." For most of human history, we assume time was simple. Universal. Absolute. Sir Isaac Newton, one of the greatest scientific minds who ever lived, believed that time was like a cosmic river flowing at exactly the same rate everywhere. Always, forever. A second here on Earth was a second on Mars. A second near the sun was a second in the farthest reaches of the galaxy. Time was time. End of story. And that made sense. Felt right. It matched everything we could observe in our everyday lives. But then came the early 20th century, and a young Swiss patent clerk, a man who was, at the time, considered a middling student by some of his professors, sat down and thought about something almost no one had thought to question before. What would happen, he wondered, if you traveled alongside a beam of light? His name was Albert Einstein, and what he discovered didn't just change physics. It changed the nature of reality. Einstein and the elastic universe. Einstein realized something astonishing. The speed of light is constant. It never changes. No matter how fast you're moving, no matter where you are in the universe, light always travels at the same speed. About 300,000 kilometers per second. Now, that sounds like an interesting fact, the kind you might drop at a dinner party. But it has consequences so radical, so earth-shaking, that when you follow the logic all the way through, the universe becomes almost unrecognizable. Think of it this way. Imagine you're standing still, and a car drives past you at 60 kilometers per hour. Now imagine you're in another car, driving in the same direction at 40 kilometers per hour. From your perspective, that first car seems like it's only moving at 20 kilometers per hour. You've closed some of the gap. That's how speed normally works. We add and subtract. Simple math. But light doesn't play by those rules. It doesn't matter how fast you're moving, toward the light or away from it. It always appears to travel at the same speed relative to you. Always. Now think about what that means. If two people moving at very different speeds both measure light traveling at the same velocity, something else has to give. Something has to stretch or compress to make the math work out. That something is time and space. Einstein showed us that time and space aren't separate things. They're woven together into a single fabric he called spacetime. And this fabric isn't rigid. It's elastic. It bends. It stretches. It warps. And the thing that warps it most powerfully is gravity. The more massive an object, the more it bends the spacetime around it. And when spacetime bends, time itself changes speed. Time in slow motion. This isn't science fiction. This has been tested, measured, confirmed. We have clocks on satellites orbiting Earth right now, the GPS satellites you rely on every time you use your phone's navigation, that run at a different rate than clocks on the ground. The difference is tiny, just a few microseconds per day. But it's real. And the engineers who built GPS had to account for Einstein's relativity in the software, or your GPS would drift by kilometers every single day. So here's the mind-bending takeaway from part 1. Time is not a fixed, universal constant. It's a local experience. It depends on how fast you're moving, and it depends on how much gravity is pulling on you. The stronger the gravity, the slower time runs. The faster you move, the slower time runs. And in the universe, there are places where gravity becomes so intense, so incomprehensibly powerful, that time slows to a crawl, or stops, or breaks. But we'll get there. First, let's look up. Did you know? The GPS satellites orbiting Earth experience time about 38 microseconds faster per day than clocks on the ground. A combination of altitude, less gravity equals faster time, and orbital speed, faster motion equals slower time. Engineers had to program in a correction based on Einstein's equations. Without that correction, GPS would be off by about 11 kilometers every day. Einstein's theory of relativity isn't abstract physics, it's inside your phone. Part 2. Stars as cosmic clocks. The sky's oldest storytellers. Look up at the night sky on a clear night, away from city lights, somewhere dark and quiet, and what you're really looking at is a gallery of time. Every single point of light you see is a star. And every single one of those stars is at a different age, a different stage of life. Some of them are infants just a few million years old. Some are middle-aged, stable and steady. Some are ancient billions of years old, burning the last of their fuel in a long, slow, dignified twilight. When you look at starlight, you're not seeing what the star looks like now. You're seeing what it looked like when the light left it. The nearest star to our solar system, Proxima Centauri, is about 4.2 light-years away. That means the light entering your eyes right now left that star 4.2 years ago. The bright star Sirius, which you've probably seen blazing in the winter sky, is about 8.6 light-years away. When you look at Sirius, you're looking 8.6 years into the past. And some of the stars visible to the naked eye are hundreds or even thousands of light-years away. The light reaching your eyes from those distant suns began its journey before some of the oldest buildings on Earth were built. The night sky is a time machine, and the stars inside it are clocks. How a star is born. To understand stars as timekeepers, we need to understand how they work. So let's begin at the very beginning. Somewhere in a vast, cold cloud of hydrogen gas, called a nebula, something disturbs the peace. Maybe it's the shockwave from a nearby star that exploded. Maybe it's just the slow, patient pull of gravity. But clumps begin to form in the cloud. Denser regions attract more gas. The gas pulls inward. The cloud collapses. As it collapses, it heats up. Just like a bicycle pump gets warm when you compress air through it, compressing gas generates heat. The collapsing cloud spins faster as it contracts. Imagine a figure skater pulling in their arms during a spin. It flattens into a disc. At the center, the temperature and pressure climb to extraordinary levels. Millions of degrees. And then something incredible happens. Hydrogen atoms, stripped of their electrons in the searing heat, reduced to their bare nuclei, begin to collide with enough force to fuse together. Hydrogen atoms fuse into helium. And in the process, a tiny amount of mass converts directly into energy. Pure, radiant energy, pouring outward in every direction. A star is born. This process, nuclear fusion, is the heartbeat of a star. It's the source of all its light, all its heat, all its power. And for a star like our sun, it will continue burning for an almost incomprehensible length of time. The sun's lifespan and yours. Our sun has been burning for about 4.6 billion years. It contains enough hydrogen fuel to burn for roughly another 5 billion years before it begins to change. In cosmic terms, our sun is a healthy middle-aged adult, about halfway through its life. Let's put that in perspective. 5 billion years ago, there was no Earth, no solar system, no life. The very atoms in your body were inside other stars that lived and died before the sun was born. You are made of stellar leftovers. Quite literally, you are stardust. And 5 billion years from now, when the sun has used up its hydrogen fuel, it will begin to change. It will swell into a red giant, expanding outward until it engulfs Mercury, then Venus, and possibly Earth itself. Then, over millions of years, it will shed its outer layers in a beautiful, glowing shell called a planetary nebula, leaving behind a tiny, dense, cooling remnant called a white dwarf. The white dwarf will cool slowly over billions of years, until it becomes nothing more than a cold, dark cinder drifting in space. A black dwarf, a gravestone. That is the life cycle of a star like our sun born from gas, burning for billions of years, dying in beauty and silence. But bigger stars have more dramatic endings, and their deaths hold some of the most jaw-dropping secrets in the cosmos. Measuring the age of stars. So how do scientists actually know how old a star is? How can you look at a pinpoint of light billions of light years away and say with confidence, that star is 3 billion years old? The answer is in the light itself. When you pass sunlight through a prism, you get a rainbow, the full spectrum of visible light. But if you look very carefully at that rainbow, you'll notice something. There are dark lines running through it. Thin, precise, dark lines at very specific positions in the spectrum. These are called absorption lines, and they work like a fingerprint. Every element in the universe, hydrogen, helium, carbon, iron, gold, absorbs light at very precise wavelengths. When light passes through the outer layers of a star, the elements there absorb specific colors, creating those dark lines. By reading these lines, scientists can determine exactly what elements a star is made of. And the ratio of elements tells a story. A very young star is almost entirely hydrogen and helium. Those are the most abundant elements in the universe. But as a star ages, it fuses hydrogen into helium, then helium into carbon, carbon into oxygen, and so on up the periodic table. The proportion of heavier elements increases over time. Beyond that, scientists use something called the Hertzsprung-Russell diagram, a chart that plots stars by their temperature and brightness, to understand where a star is in its life cycle. A star's position on this chart tells you its age the way a doctor can estimate a person's age from an X-ray by looking at bone density and structure. We don't just guess how old stars are. We read it from the light. The universe has been keeping records all along. The supernovae when stars explode. Now, let's talk about the most violent, spectacular events in the observable universe. The death of a massive star. When a star much larger than our sun, say 10 or 20 times more massive, runs out of fuel, it doesn't gently puff up and fade. Collapses. In a fraction of a second, the entire core of the star implodes under its own gravity, creating pressures and temperatures beyond imagination. And then it bounces, releasing an explosion so powerful that, for a brief moment, that single star outshines the entire galaxy it lives in. This is a supernova, and they are breathtaking. A supernova releases more energy in a few seconds than our sun will release in its entire 10 billion-year lifetime. It scatters all the elements the star spent its life creating: carbon, oxygen, silicon, iron, and dozens of others, out into space. These elements eventually become part of new nebulae, new star systems, new planets. And sometimes, just sometimes, on new planets like ours, those elements become the building blocks of life. Every atom of carbon in your body was forged in the heart of a star that died before the sun was born. Every iron atom in your blood was created in a stellar explosion billions of years ago. We are not just observers of the cosmos. We are participants. We are the universe looking at itself. Here's something incredible. In 185 AD, Chinese astronomers recorded the appearance of a guest star in the night sky, a bright new light that wasn't there before. What they were witnessing was a supernova explosion, the death throes of a massive star about 8,200 light-years away. The light from that explosion had been traveling for over 8,000 years before it reached Earth and was recorded in an ancient Chinese manuscript. Today, we can point to the exact remnant of that explosion, a glowing shell of gas called RCW-86, still expanding outward through space. Pulsars, the universe's most precise clocks. After a massive star explodes in a supernova, what's left at its core? Sometimes nothing survives. The collapse is total and a black hole is born, but we'll return to those. But other times, the core survives as one of the most extraordinary objects in the known universe. A neutron star. A neutron star is what you get when the gravity of the collapsing core is so intense that it crushes protons and electrons together into neutrons, compressing the entire core of a star that was once larger than our sun into a sphere about 20 kilometers across, roughly the size of a city. Think about that for a moment. The mass of the sun, which is enormous enough that you could fit over 1 million Earths inside it, compressed into something smaller than Los Angeles. The density is so extreme that a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Now, remember that figure skater analogy? When a star's core collapses, it spins faster, much, much faster. Some neutron stars rotate hundreds of times per second. And as they spin, they emit beams of radio waves from their magnetic poles, like cosmic lighthouses sweeping their beams through space. When those beams happen to sweep past Earth with each rotation, we detect a pulse. A regular, precisely timed pulse. These are called pulsars, and their timing is extraordinary. The most stable pulsars, called millisecond pulsars because they rotate hundreds of times per millisecond, tick with such remarkable precision that they rival and sometimes surpass the best atomic clocks we've ever built on Earth. The most precise atomic clocks lose about 1 second every 300 million years. Some pulsars are accurate to within 1 microsecond per year over decades. The universe built clocks that make our best human technology look rough and imprecise by comparison. Scientists use these pulsars as reference points for measuring time across the cosmos. Arrays of pulsars spread across the galaxy form a kind of natural GPS for the universe, a timing network built from spinning stellar corpses, ticking with quiet, machine-like perfection. And here's a thought that deserves a moment's pause. These pulsars were created in the most violent explosions in the universe, born in fire and catastrophe, and yet they tick with more accuracy than anything human hands have ever crafted. Violence in the cosmos sometimes creates extraordinary precision. Did you know? The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell. The signal was so regular, a perfect pulse every 1.3 seconds, that she and her supervisor initially joked that it might be a signal from an alien civilization. They called it LGM-1, for Little Green Men. It was only after discovering more of these objects that they realized what they actually were. The ticking hearts of stellar remnants. Part 3. Black holes. Where time breaks. The point of no return. Now we arrive at the strangest, most awe-inspiring, most mind-bending objects in the universe. Black holes. You've probably heard the word. Maybe you've seen dramatic visualizations of them in movies or on the news. But I want to go deeper than the images. I want to tell you what a black hole actually does to time, because that's where things get truly extraordinary. Let's start at the beginning. Where do black holes come from? We've already talked about neutron stars, the dense, spinning remnants of massive stars that explode in supernovae. But if the collapsing core is heavy enough, roughly 3 times the mass of the sun or more, even the pressure of neutrons packed tightly together isn't enough to stop the collapse. Gravity wins completely. The core collapses past neutron star density, past any known state of matter. It collapses to a point, a mathematical singularity, where density becomes infinite and our equations for describing reality simply stop working. Around the singularity, space is curved so severely, gravity is so strong, that at a certain radius, the escape velocity, the speed you'd need to travel to escape the gravitational pull, exceeds the speed of light itself. And since nothing, absolutely nothing, can travel faster than light, Anything that crosses that boundary can never escape. This boundary is called the event horizon. It is not a physical surface. There's no wall. There's no barrier you'd feel. It's just a location in space, a mathematical threshold. But crossing it is irreversible. Once you're inside the event horizon, you are, from the perspective of the outside universe, gone. Not just stuck. Not just very far away. Gone. A thought experiment at the edge of everything. Let's use our imaginations. Let's say you're an astronaut, bold, reckless, curious beyond all reason, and you've decided to fly toward a black hole. One of the stellar mass variety, roughly 10 times the mass of our sun. As you approach from a great distance, nothing seems unusual. You can see the black hole only by what surrounds it. A bright disk of gas and dust spiraling inward, glowing hot and white and furious, called the accretion disk. The black hole itself is visible only as a dark, perfect circle, a shadow, in the center of all that light. You're watching from inside your spacecraft and you have a companion, a friend who stayed behind, watching you through a powerful telescope. As you get closer, something strange begins to happen, though you might not notice it yourself. From your friend's perspective, watching through the telescope, you are slowing down. Not because your engines are failing, not because you've changed course, but because time itself around you is running more slowly. The stronger the gravity, the slower time passes. Your friend watches you approach the event horizon. But as you get closer and closer, your movements seem to slow. Your waving hand moves in slow motion. The light reflected from your spacecraft becomes redder, shifted toward the red end of the spectrum by the immense gravitational field, the same way a sound's pitch changes as the source moves away. This is called gravitational redshift. To your friend, you never quite reach the event horizon. You appear to slow and slow and slow, becoming dimmer, redder, more ghostly, until you seem to freeze at the edge like a photograph. An eternal silhouette at the threshold. But here's the twist. From your own perspective, you cross the event horizon without fanfare. There's no flash of light. No alarm. No sudden sensation. You simply cross a threshold in space and time. In fact, for a large enough black hole, you might not even notice anything unusual at the moment of crossing. Same event. Two completely different experiences of time. That is gravitational time dilation. And it is real. What happens inside? Once you're past the event horizon, a very specific, very final fate awaits. Gravity pulls you toward the singularity. But it doesn't pull evenly. The gravity closer to the singularity is stronger than the gravity slightly further away. So the side of your body closer to the center is being pulled harder than the side further away. This difference in gravitational force across your body is called a tidal force. And for a stellar mass black hole, these tidal forces become so extreme that they would stretch your body out feet first if you went feet first, like cosmic taffy. Physicists have a name for this process. They call it spaghettification, which, given the circumstances, is a surprisingly charming word. As you fall toward the singularity, time from the outside universe appears to speed up. Every second of your experience corresponds to longer and longer stretches of time in the external universe. By the time you approach the singularity, billions of years could have passed outside. You wouldn't see any of that. You'd just be falling. And then you'd reach the singularity, where all our current understanding of physics breaks down entirely. We don't know what happens at a singularity. Truly, we don't know. The equations we use to describe reality, general relativity, quantum mechanics, give nonsensical answers when applied to that point. It's as if the universe has a secret there, written in a language we haven't learned yet, the supermassive kind. Everything I've described about stellar black holes, roughly a few to a few dozen times the mass of our sun, is already extraordinary. But our galaxy, the Milky Way, has a secret at its center. At the heart of the Milky Way, about 26,000 light-years from Earth, sits a black hole called Sagittarius A star. And it is not small. Sagittarius A star has a mass of about 4 million times the mass of our sun. It is supermassive. And nearly every large galaxy we've studied appears to have one of these giants at its center. In 2019, astronomers made history, using a global network of radio telescopes linked together to form a virtual telescope the size of the entire Earth. a project called the Event Horizon Telescope. They captured the first ever photograph of a black hole's shadow. Not Sagittarius A star, but the supermassive black hole at the center of a galaxy called M87, some 55 million light-years away. The image showed a glowing ring of superheated gas, and in the center, a dark circle, the shadow of the event horizon. For the first time, humanity had an actual photograph of the place where time breaks. And in 2022, they did it again, this time capturing Sagittarius A star itself. The black hole at the center of our own galaxy, finally visible to human eyes. Near Sagittarius A star, time is not like time here. A clock sitting close to its event horizon would run so slowly that 1 year there would correspond to thousands of years on Earth. Time isn't just slower there. It's almost frozen. If you stood far enough away and watched, which would still be extraordinarily dangerous, the nearby region would seem still, silent, like the universe holding its breath. Here's something incredible. In the movie Interstellar, the fictional planet Miller orbits so close to a massive black hole that 1 hour on the planet's surface equals 7 years back on Earth. This isn't just Hollywood fantasy. The screenwriters consulted extensively with theoretical physicist Kip Thorne, who actually won the Nobel Prize in Physics in 2017 for his work on gravitational waves, to make the physics as accurate as possible. The movie's visualization of the black hole was so scientifically precise that it contributed to new research papers on how light bends around these objects. Part 4. The Rhythm of Space. The cosmos has a heartbeat. We've explored the lives and deaths of stars. We've stood at the edge of time itself at the brink of a black hole. Now let's zoom out. Way out, because the universe doesn't just contain extraordinary objects. It has a rhythm, pattern, a pulse. Think of it like music. Individual notes are important, but the music is made by how those notes relate to each other, how they move in time together. The cosmos is filled with motion, circular, spiral, oscillating, expanding motion, and this motion has a beat. Orbital motion, the original clockwork. The most ancient and reliable rhythm that humans have ever observed is orbital motion. Earth orbits the Sun. We've been doing it for 4.6 billion years, and our calendar is built on that orbit. 1 year is the time it takes Earth to complete one journey around the Sun. It's so precise that we can predict exactly where Earth will be in 10,000 years, or where it was 10,000 years ago. But Earth isn't the only thing orbiting. The Moon orbits Earth. The planets orbit the Sun. The Sun orbits the center of the Milky Way. The Milky Way and the Andromeda Galaxy orbit each other in a slow, graceful spiral that will end, in about 4.5 billion years, in a spectacular collision and merger of the two galaxies. Everything in the universe at every scale is in motion, and much of that motion is orbital, curved paths defined by gravity. Newton gave us the equations to describe this. He showed that the same force that pulls an apple from a tree also holds the moon in its orbit. The universe's rhythms, at their heart, are the rhythms of gravity. But gravity isn't just a passive force holding things in place. It can shake things. It can send ripples through the very fabric of spacetime itself. Gravitational waves, the sound of space. On September 14, 2015, at exactly 5:51 in the morning, U.S. Eastern Time, something incredible happened at a facility in Louisiana called LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 incredibly precise laser beams, each running through tunnels 4 kilometers long, detected a tiny disturbance. Not a vibration from traffic. Not wind. Not an earthquake. The ground, the tunnels, the very atoms of the detector stretched and then compressed by an almost unimaginably small amount. Less than 1,000th the diameter of a single proton. It lasted only a fraction of a second. But in that fraction of a second, humanity detected something for the very first time. A gravitational wave. So what is a gravitational wave? Remember how massive objects bend spacetime, the fabric of the universe. Well, when massive objects accelerate through that fabric, they don't just sit there bending it. They send ripples outward, like a stone dropped into still water. The disturbance that LIGO detected had traveled 1.3 billion light-years, from a pair of black holes, each about 30 times the mass of our Sun, that had been spiraling toward each other for eons and finally collided. In the final fraction of a second before they merged, they were moving at nearly half the speed of light, radiating more energy in gravitational waves than all the stars in the observable universe combined radiate in light. That collision happened 1.3 billion years ago, before multicellular life existed on Earth. And the ripple from that collision reached us in 2015, still carrying the signature of what happened, like an echo from before the age of animals. When physicists at LIGO translated the gravitational wave data into sound, by shifting its frequency into the audible range, it made a noise, a brief chirp, rising in pitch, and then silence. That chirp was the sound of two black holes merging, the sound of the most violent event in the modern universe. And we heard it. Since that first detection, LIGO and its partner observatories around the world have detected dozens of gravitational wave events, merging black holes, merging neutron stars, and events we're still working to classify. Every detection is a new way of listening to the universe. We spent thousands of years looking at the cosmos. Now we're listening to it, and its voice is extraordinary. Did you know? When two neutron stars merged in 2017, an event detected by both gravitational waves and light simultaneously, it confirmed something that had long been theorized. Neutron star collisions are the forge where gold, platinum, and other heavy elements are created. When you wear a gold ring, you're wearing a piece of jewelry forged in a collision between two dead stars, billions of years ago. The romantic notion of stars being the origin of all things is, quite literally, true. The expanding universe, time moving in one direction. Now for perhaps the most extraordinary rhythm of all, the expansion of the universe itself. In the early 20th century, astronomers began noticing something strange about distant galaxies. When they analyzed the light from far-off galaxies, they found it was shifted toward the red end of the spectrum, what astronomers call redshift. And the further away a galaxy was, the more its light was redshifted. This is the same principle as the Doppler effect, which you've probably experienced with sound. When an ambulance approaches you, the pitch of its siren sounds higher. When it moves away, the pitch drops. This is because the sound waves are being compressed when the source moves toward you, and stretched when it moves away. When light is stretched, it shifts toward the red end of the spectrum. So distant galaxies were moving away from us. All of them, in every direction. The only explanation is that space itself is expanding. Not the galaxies moving through space, but the space between galaxies growing. Like dots drawn on a balloon, as you inflate the balloon, every dot moves away from every other dot. Not because the dots are moving, but because the surface between them is expanding. This expansion is one of the universe's most fundamental rhythms. And it's not slowing down. If anything, it's speeding up, driven by a mysterious energy we call dark energy, which we understand so poorly that the name dark energy is really just an admission that we have no idea what it is. If you trace this expansion backward in time, like rewinding a film, the universe gets smaller and smaller, hotter and hotter, denser and denser, until you reach a beginning. A point of origin that we call the Big Bang, roughly 13.8 billion years ago. From that single explosive origin point, the universe has been expanding, cooling, forming structure, atoms, stars, galaxies, planets, life, for almost 14 billion years. And time has been ticking since that first moment. The cosmic calendar. The astronomer Carl Sagan once proposed a beautiful thought experiment called the cosmic calendar. Take the entire history of the universe, 13.8 billion years, and compress it into a single calendar year. Each month represents just over a billion years. Each day represents about 38 million years. On this calendar, the Big Bang happens at midnight on January 1st. Our solar system forms around September 2nd. The first life on Earth appears around September 21st. The first multicellular organisms, November 5th. Dinosaurs appear on December 25th. And all of recorded human history, every war, every invention, every song, every poem, every scientific discovery, every empire, every love story, happens in the last 14 seconds before midnight on December 31st. All of history, in 14 seconds. That is our place on the timeline of the universe. And yet, improbably, wonderfully, we are here, and we are asking questions about it. Here's something incredible. The observable universe, the portion we can actually see, is about 93 billion light-years across. But this doesn't mean the universe itself is only that size. Because the universe has been expanding since the Big Bang, and it expanded faster than light in the very early universe, there are regions of the universe from which light simply hasn't had time to reach us yet. The total universe might be infinitely larger than what we can observe. We are looking at the cosmos through a window, and the window is smaller than the room. The grand synthesis, bringing it all together, time, stars, and you, we've traveled a long way together. We started by questioning something as familiar as time itself, and discovered that it isn't fixed. It bends. It stretches. It slows in the grip of gravity and quickens in the emptiness of space. We walked through the birth of stars, great columns of gas collapsing under their own weight, igniting in nuclear fire, burning for billions of years. We learned that stars are clocks, their ages written in the frequencies of light they emit. We met pulsars, spinning neutron stars of extraordinary density, ticking with a precision that surpasses our best technology. We stood at the edge of black holes, those most extreme objects in the universe, and contemplated what happens to time there. Not as a metaphor, not as poetry. Literally, actually, measurably, time slows, warps, and at the singularity, does something we don't yet have the language to describe. We felt the rhythm of the cosmos itself. The orbital dances, the gravitational ripples spreading outward from violent collisions across billions of light-years, the slow exhalation of the expanding universe. Growing, always growing. And now I want to sit with you in this ending for a moment. You are the universe becoming aware of itself. There's a phrase that the astrophysicist Neil deGrasse Tyson likes to use: we are stardust, contemplating the stars. But let's go deeper than the poetry. Every atom in your body, the carbon in your DNA, the calcium in your bones, the iron in your blood, was forged in a stellar furnace. Some of those atoms came from stars that died billions of years ago, scattered their material into space, and were incorporated into the cloud of gas and dust that eventually became our solar system. You are, in the most literal sense possible, made of stars. And now those atoms, that ancient, recycled, star-forged material, have organized itself into a form complex enough to ask questions, to build telescopes, to decode the fingerprints in starlight and determine the age of objects billions of light-years away, to build instruments sensitive enough to hear the chirp of two black holes merging 1.3 billion years ago. The universe has been ticking away since the Big Bang, 13.8 billion years of cosmic time, stars living and dying, black holes bending space-time, galaxies rotating in their slow, majestic spirals. And in one tiny corner of one unremarkable spiral galaxy, on a small rocky planet orbiting a middle-aged yellow star, matter became aware of itself. We are how the universe knows about itself. Every time you look up at the night sky and feel that pull, that instinctive human wonder at the vast darkness and the brilliant points of light, you are the cosmos experiencing itself. The atoms that make up your eyes looking at the atoms that make up the stars, connected by light that has been traveling for longer than life has existed on Earth. What this means for time. Here's the final thought I want to leave you with. We open by asking, what if time doesn't tick the same everywhere? Now you know it doesn't. Near a black hole, time creeps. In the emptiness far from any mass, time flows more freely. For a particle of light, moving at the ultimate speed limit of the universe, no time passes at all. Light doesn't experience duration. A photon emitted from a star a billion light-years away and one that reaches your eye a moment later, from the photon's perspective, those two events are simultaneous. The journey takes no time. Time is not an absolute river, flowing at the same rate for everything everywhere. It is local, personal, relative. And yet, here is the astonishing thing. Despite all of this, the universe has rhythm. It has patterns. Stars live and die on timescales we can measure. Pulsars tick with extraordinary regularity. Gravitational waves ripple outward at the speed of light. The universe expands at a rate we can calculate. Galaxies orbit each other on schedules that persist across billions of years. The cosmos has time. It just doesn't have time the way we first imagined it. It has something richer, something stranger, something that makes our old, simple notion of time, A steady clock ticking the same beat everywhere, seem almost quaint. A final thought. Somewhere in the universe right now, a star is being born. A clump of gas is collapsing, spinning faster, heating up, and on the verge of igniting its first nuclear reaction. The light from that birth won't reach Earth for millions of years. Somewhere in the universe right now, a massive star is in its final hours, its core collapsing in a catastrophic implosion that will result in either a neutron star or a black hole. The shock wave rippling outward will scatter the products of a lifetime of nuclear burning into space. That material will, someday, become part of new stars, new worlds, new possibilities. Somewhere in the universe right now, two neutron stars are spiraling toward each other in a gravitational waltz that has been tightening for millions of years. When they finally collide, the gold and platinum they forge will become part of the universe's chemical inventory. Someday, some of it might end up on someone's finger. And somewhere in the universe right now, a black hole is doing what black holes do, silently warping space-time, bending light into rings, slowing time to an almost perfect stillness at its edge. Patient.
Permanent.
Absolute. All of this is happening right now, simultaneously, across the vast, incomprehensible span of 93 billion observable light-years. And you, small, brief, miraculous you, are aware of it. In the grand cosmic calendar of 13.8 billion years, your life is an instant. A single beat in an ancient, magnificent, ongoing rhythm. But you're in the rhythm. You're part of it. The same forces that govern the spinning of pulsars and the orbits of galaxies govern the beating of your heart. The same matter that has cycled through stellar furnaces across billions of years is, right now, thinking these thoughts. The universe is not indifferent to you. It made you, from its own substance, across its own time, through a process of almost unimaginable complexity and beauty. It made something that can look back at it and say, I see you. I wonder about you. I want to understand you. And in that wondering, in that reaching out across the dark with curiosity and awe, something remarkable happens. The universe, through us, wonders about itself. And that might be the most beautiful rhythm of all. Thank you for traveling with me today. If this journey sparked something in you, a question, a wonder, a need to look up at the night sky a little differently, then the cosmos has done its job. And so have we. Until next time, keep looking up.